Hello students, so in this session we are going to study about the topic calorimetry. Okay, calorimetry. So the principle of calorimetry is, okay, heat lost is equal to heat gained. That is, if there are in a system, if there are two entities or two bodies or two particles, or if a body and the surrounding, then based on the temperature in the two entities, heat will be transferred from the body at a high temperature to the body at a low temperature. Okay, so heat will be transferred from the body at a high temperature to the body at a low temperature, and finally it will reach at a thermal equilibrium. Okay, so heat lost is equal to heat gained. This is the principle of calorimetry. So heat lost by, we can say, hot body is equal to heat gained by the cold body. Okay, heat lost is equal to heat gained. This is what is the principle of calorimetry, but the real meaning is heat lost by the hot body is equal to heat gained by the cold body. Clear? This is the principle of calorimetry. As in the beginning of the chapter, as we discussed, suppose if we keep a cup of tea on a table, okay, the temperature of the tea will come down and heat will be transferred to the surroundings. So finally the surrounding temperature and the temperature of the tea both will be equal. If we keep a cup of ice in a place, what will happen? The temperature of the ice will increase. It may become water based on the surrounding temperature, and finally the temperature of the surrounding and temperature of that ice, okay, that will become equal. So first case, in the case of hot tea, temperature is more in the tea, so heat is lost by the tea and heat will be gained by the surrounding. When we keep a cup of ice, there the temperature of ice is less, so surrounding will give the heat towards the ice and temperature of ice will be increased. So heat lost by the surrounding, heat will be gained by the what? Ice. So this is how the mechanism works, and till the thermal equilibrium is attained, this process will continue. Okay, thermal equilibrium will be attained. Thermal equilibrium will be attained. Clear? Okay, now one by one we will understand this. Suppose if we take a container, and this, suppose if this is a sealed container, okay, sealed container, and I am just naming this wall as adiabatic wall. What do you mean by adiabatic wall? Adiabatic wall is nothing but it will not allow heat to enter or heat to go out. Okay, will not allow heat to pass. Okay, so first time I am using this word adiabatic wall. Now you can understand adiabatic wall is a kind of wall which will not allow heat to enter or heat to leave, energy to enter, energy to leave. Okay, simple example, flask. Okay, a perfect flask or ideal flask, we can say no way heat will enter or leave. Okay, so inside, if we are putting three bodies, okay, this is body A, this is body B, and this is body C. Its temperature is TA, its temperature is TB, its temperature is TC. Okay, this is initially just after putting this thing. Okay, body is maintained at temperature, put it inside, another body is kept at another temperature, put it inside, likewise 3-1. Now if we keep it for some time, later after some time what will happen? Okay, heat will be transferred between them. Finally, this C, this A, and this B, everyone will have one temperature, that is T. The temperature of C, the temperature of body A, temperature of body B, everything will be same. Okay, T. Okay, not TC. Okay, T. Okay, fine. So here, whichever is having less temperature, that will accept heat. Whichever is having more temperature, that will reject heat. Likewise, between them, this heat transfer will happen, and finally they will attain thermal equilibrium. So this process is a spontaneous process. Spontaneous process means this will happen by its own. Okay, we need not do any work. It will happen till it attain thermal equilibrium. Clear? So okay, so this is the introduction of this topic. Clear? Fine. So now, due to this process, due to this heat exchange, okay, certain things will happen, certain results will be there. Okay, those results we will analyze now, we will see it now, and these things we are going to use throughout this topic. Okay, so I would like to take a container and I have taken ice. Okay, say for example this is 10 degree Celsius, minus 10 degree Celsius. Okay, I have taken ice at a minus 10 degree Celsius here. Now I am applying heat here. What will happen? This ice will accept heat happily, and it will convert into, first what will happen? The temperature of ice will increase. And in the next stage, what will happen? Temperature of ice will increase, that is minus 10 degree Celsius will become minus 9, minus 8. Likewise, initially, okay, in the first transformation, this will become ice at 0 degree Celsius, step by step. So what will happen? Its temperature will increase. Now we are supplying heat continuously. This was ice at minus 10 degree Celsius. Now this is ice at 0 degree Celsius. Now it will take what? It will take some heat and it will change its temperature. Okay, some heat is used here. Okay, now one thing which I would like to explain here, the heat used to increase its temperature, okay, per mass, okay, per unit mass. Okay, for per unit degree change in temperature is called the specific heat capacity. Okay, so here in this process we are using specific heat capacity. Okay, so this is denoted by C or S. What is specific heat capacity? The heat required to change the temperature of unit mass of a substance by unit or we can say by 1 degree Celsius, by 1 degree Celsius. Okay, so specific heat capacity, okay, or specific heat is nothing but the heat required to change the temperature of unit mass of a substance by 1 degree Celsius. Okay, clear? So if I need to convert 1 gram of ice, okay, if I need to convert or if I need to raise the temperature of 1 gram of ice by 1 degree Celsius, how much is the specific heat? Okay, that is the specific heat capacity of this ice. Okay, so we will be discussing this a lot. You will become comfortable in this, I assure you that. Just now we are moving with the introduction. So here, how much is the specific heat capacity of the ice? Okay, so that much will be taken by this ice and that will convert into ice at 0 degree Celsius. Here the change in temperature I have taken is 10. For 5 degrees Celsius, that much heat. For 10 degrees Celsius, that much heat. Okay, likewise. Clear? Now, what is the specific heat capacity? C is actually the heat required to change the temperature of unit mass of a substance. Okay, so the temperature, the heat required. So the heat required to change the temperature of unit mass of a substance by 1 degree Celsius. So for unit mass means, suppose if it is 5 gram, in order to understand the heat for unit mass, we need to divide by its mass. Okay, so here the temperature changes by 1 degree Celsius. So if there is T degree Celsius change, delta T change is there, that is from 5 to 10 or 0 to 10, 0 to 30, then for 1 degree we need to understand, then we will have to here delta theta. I am using here change in temperature as instead of T I am going to put here delta theta. So this is what is specific heat capacity. Specific heat capacity is the heat required per unit mass per unit degree change in temperature. The heat required per unit mass per unit degree change in temperature. Okay, that is what is specific heat. Now if mass is m, in order to find for unit mass we have divided with m. In order to find the unit degree change in temperature we have divided with delta theta. Now the total heat required for m mass of substance will be what? I need to multiply with here if it is q. Okay, then in order to, sorry, okay, so this q is for this C is for 1 gram for 1 degree change. Now suppose if I need to find for m mass, m gram or m kilogram for delta theta change in temperature. So I need to multiply the specific heat with the mass into C into for delta change in temperature I need to multiply with delta theta. So Q is equal to mc delta theta. Q is equal to mc delta theta for m mass for delta theta temperature change. Okay, how much heat is required? Clear? Okay, so for 1 gram for 1 degree change we say specific heat. For m mass and for delta theta change we multiply with that mass and we multiply with that change in temperature. So total heat required is mc delta theta. Okay, now here in this topic we can use SI unit. When we use SI unit, the numbers will be a little bit bigger values and calculations will become more. So mostly in the questions also, in JEE as well as Neet questions also, multiple choice questions where calculation should take only less time, we will be getting the values in calories. So we will be solving all these problems in calories only. So specific heat capacity of ice, specific heat capacity of water, steam, all these things will be given in the question. Okay, but I shall tell you now. So specific heat capacity of ice is nothing but half, 1/2. Specific heat capacity of ice is 1/2 calorie per gram degree Celsius. Okay, calorie per gram degree Celsius. We do it in gram. Okay, only very few questions we will be using kilogram, Kelvin and all. Change in temperature for Kelvin as well as for degree Celsius both are same, so it will not affect us. Okay, fine, hope you understood. Okay, specific heat capacity, the total energy required. Okay, now shall I erase this? Please pause the screen and note it down. Okay, okay, now I should remember this mc delta theta. Okay, Q is equal to mc delta theta, C is half. All these things you will become comfortable once we do problems. Okay, so here what is the heat? What is the heat taken by the ice in this process? This is mc delta theta. Okay, suppose example, okay, if this is 5 gram of ice, if this is 5 gram of ice and I am converting, the change in temperature is how much? 10 degrees Celsius. Okay, so in this case the total heat required will be mc delta theta. So this is going to be 5 gram into the specific heat capacity of ice in calories is 1/2 into delta theta, here it is 10. Okay, so if this will become 25 calories. So 25 calories heat, 25 calories heat is required to convert 5 gram of ice at a minus 10 degrees Celsius into 5 gram of ice at a 0 degrees Celsius. Clear? Okay, hope you understood. Okay, so this is an example. Okay, done? Clear? Shall I erase this? Okay. Now, what is the next process? Still we are applying heat. Next process is this will start converting into water. So what will happen? Okay, half ice and some amount of water will be there. We are applying heat. So in this process, okay, this is nothing but change of state. So heat is applied, heat is still applying. What is happening here? Change of state, that is ice to water conversion is going on. In this thing, what is happening? Change in temperature, change in temperature. Okay, so the thing is, in this process, till the complete ice is till the complete ice gets converted into water, till that there is no change in temperature. Okay, so this is minus 10 degrees Celsius, no change in state. This is at 0 degrees Celsius. Now here also the temperature is going to be 0 degrees Celsius, and this process continues. This process will be continued. Okay, here once if it becomes full water, say for example this is 10 gram, okay, this is also 10 gram, this is now 5 gram water and 5 gram ice. Okay, now this is full 10 gram water. What is its temperature? This is 0 degrees Celsius. This is also 0 degrees Celsius. That is, the entire heat will be utilized in order to convert the state. Here the heat is utilized to increase the temperature. Here the heat will be utilized to change the state. So till it change the state completely, the heat will be utilized only for that purpose. Heat will not be utilized to change the temperature. So till it becomes 0 degrees Celsius full water, there won't be any change in temperature. Okay, there won't be any change in temperature. Okay, so the heat required to change the state is called the latent heat. So latent heat, the word meaning is nothing but hidden heat. So here I am introducing another terminology, latent heat, which is nothing but hidden heat. Okay, because the change in temperature will not be visible, change in state will be visible. So the entire heat will be utilized to change the state. Okay, so latent heat, or this is hidden heat. Okay, so we can say latent heat, the heat required to change the state of 1 gram or unit mass. Okay, unit mass. So 1 gram will be in calorie and 1 kilogram we can say in joule. Okay, so I can say heat required to change the state of unit mass, generally unit mass of a substance. Okay, so heat required to change the state of unit mass of a substance. Clear? That is what is latent heat. Hidden heat, the heat required to change the state. Temperature will not change here. Clear? Okay, so we denote using the letter L. Fine, copy this. This figure I will be continuing like this. Okay, shall I erase this? Okay, so we can say latent heat L is equal to the heat required to change the state of unit mass. So I can divide this by M. Okay, and so for M mass, for changing M kilogram or M gram into what? Another state. Okay, Q is equal to what? ML. Okay, So previously we did here Q is equal to mc delta theta for changing the temperature. Now in order to change the state, Q is equal to ml. Clear? Note it down. Okay, shall I erase this? Shall I erase this? Okay, so children, now to change the temperature, specific heat capacity, to change the state, latent heat. In latent heat of fusion, latent heat of fusion or melting. Latent heat of fusion or melting, that is, the latent heat of fusion means if water is converted into ice, that is, water is to convert water into ice, this water should deliver, or this water should eliminate, or water should reject some heat to the surrounding. Okay, so that is called the latent heat of fusion. Now for ice to become water, the ice should absorb some heat. To change the state from ice to water as well as water to ice, either it should reject heat for water to become ice, and for ice to become water, it should absorb heat. So that is what is called the latent heat of fusion. This fusion is what? Fusion is water to ice. Okay, so heat rejection, some heat should be delivered to outside. So latent heat of melting means water is converted into ice. So sorry, ice is converted into water. So this process is ice to water. Okay, it should absorb heat. So for both the latent heat of fusion, latent heat of melting, both will be same. One is nothing but rejection of energy or elimination of energy. One is nothing but absorption of energy. So its value is 80 calorie per gram. Okay, this is latent heat of fusion and latent heat of melting. Okay, 80 calorie per gram. In joule, its value will be bit higher, and there will be calculations also. Okay, so you can remember this, that anyway that will be given in the question also. Okay, latent heat of fusion or latent heat of melting. Clear? Shall I erase this part? Water to ice, ice to water, note it down. Okay. Now along with this I am going to write latent heat of condensation, okay, in bracket vaporization. Okay, both are same. So this is actual value is 536. We are going to use 540 calorie per gram for our calculation easiness. Okay, otherwise it will take a lot of time, there are chances for mistakes, so roughly we will be taking 540. Condensation and vaporization are not same, but this value for vaporization and condensation are same. That is why I have given in the bracket. So what is condensation? Condensation is nothing but when steam is converted into water. When steam is converted into water, just like water is converted into ice, same way steam can convert into water by eliminating energy, by rejecting energy, or by taking out energy from it. Okay, by eliminating energy from it. Okay, so this is what is condensation, steam to water. What is vaporization? Vaporization is water to steam. Okay, so how water can become steam? By absorbing heat. When it absorbs heat, water will become steam. When it rejects heat, steam will become water. Either absorption or rejection, but the latent heat for that is same. Okay, 540. Clear? I will summarize this. First you note it down. Clear? Okay. Fine. Okay. So here again we are supplying heat. Now this became what? 10 gram of water. It was first it was 10 gram of ice. 10 gram of ice. Now it became 5 gram of ice plus first it was 10 gram of ice at minus 10 degrees Celsius. Then it became 10 gram of ice at 0 degrees Celsius. Then it starts converting into water. 5 gram of ice, 5 gram of water. Now it is completely converted into water. So how much heat is utilized here? Q is equal to ml. Q is equal to ml. Is there any change in temperature between these two states? No change in temperature. This is also 0 degrees Celsius. This is also 0 degrees Celsius. Entire heat will be utilized in order to convert its change, converts its state. Okay, state. It is getting from solid state to liquid state. So entire heat is utilized there. Okay, one business is going on here. So entire money will be utilized there. They will not spend money on some other thing. Okay, full concentration here. So there is no change in temperature. Entire work is changing the state. So if it is ml, okay, example, suppose 10 gram of water, 10 gram of ice, we need to convert into 10 gram of water. Okay, then how much will be the total heat required? Nothing but ml. What is m? M is 10 gram. Latent heat of fusion or latent heat of melting is what? 10 into 540. So I could say 5400 calories. Okay, so to convert ice into water, 5400 calories will be what? Delivered or rejected, or it will be released. Okay, 5400 calorie will be released. Clear or what? Okay, suppose if we need to convert 10 gram of water to 10 gram of ice, then what will happen? Again same value will come, but 5400 calorie will be absorbed. Clear? Are you able to understand? 5400 calorie will be absorbed and converted into water. Fine? Note it down. Okay, now what is the next possibility? Now this is completely water at 0 degrees Celsius. Now again if we apply heat, okay, what can happen? Now it is completely converted into water. Now next possibility is it can become water at 50 degrees Celsius or 25 degrees Celsius, 50 or 25 degrees Celsius, 35, 45, 50. Likewise, temperature will be increased. What will happen again? This will become 100 degrees Celsius water 10 gram of water at 100 degrees Celsius. If we keep on applying heat, the temperature of the water will keep on increasing, and finally what will happen? It will become 100 degrees Celsius. So how much heat will be required for this entire process? Okay, I could say Q is equal to mc delta theta. Okay, so how much will be that? Q is equal to mass is 10 gram into C. So here I will write here C is equal to 1 by 2, okay, calorie per gram degree Celsius for ice. The specific heat capacity of ice is half. Now here the specific heat capacity of water is 1 calorie per gram degree centigrade. 1 calorie per gram degree centigrade. So if we calculate this, 10 into C is 1 into how much is the change in temperature? 0 to 100. 0 to 50 means here 50 we can give, that much heat is required. 0 to 100 we can give here 100. So totally 1000 calories are required to convert 10 gram of water from 0 degree centigrade to 100 degree centigrade. Clear? So again specific heat, because change in temperature is there. Okay, is it clear till this? Now next stage is what will happen again? After that, again once if it reaches 100 degrees Celsius, I am taking the example of water, ice, water, steam. For another material everything will be different. Okay, fine. So now what happens? This is now a part of water will be there, a part of water would have converted into steam. So we can say okay, say for example 5 gram water plus 5 gram steam is there. 5 gram steam is there. Okay, clear? Now how much energy is required for this process? So this latent heat of vaporization or latent heat of condensation is 540. Latent heat of fusion or latent heat of melting is equal to how much? 80. Okay, this is 80, this is 540. I think I have given an example of converting 10 gram of ice into 10 gram of water. I think I have taken 540. If I have taken 540, that is wrong. The total heat required for this process, that is 10 gram of ice to 10 gram of water, for this conversion total heat required is ml, that is 10 into 80. So this is going to be 800 calorie from 10 gram of ice at 0 degree Celsius to convert into 10 gram of water at 0 degree Celsius. ml, 10 into 80. This latent heat of fusion we will substitute into mass. Now in this process what will happen? 10 gram of water to convert into 5 gram of steam. Okay, 5 gram of steam. So for that the heat required is how much? ml. So 5 into 540 will be the heat required. Now suppose if we need to convert complete steam, that is I don't have space here. Okay, I will draw here. Okay, now suppose if we need to convert into 10 gram of steam at 100 degrees Celsius, then the total heat required is how much? Total heat required will be ml, that is 10 into 540. 5400 calorie will come. 5400 calorie will come. Clear or what? Okay, note it down. Pause the screen and note it down. Okay. Again, if we need to increase the temperature of steam from 100 degrees Celsius to 110 degrees Celsius, again change of state will not be there. Change in temperature will be there. Again the formula will become mc delta theta. So specific heat capacity of steam, specific heat capacity of steam, C of steam is again 1/2 calorie per gram degree centigrade, same as that of ice. Okay, in calorie, in joule they will be different. Okay, so once again I will explain this process. Okay, first minus 10 degrees Celsius ice, if we apply heat, this ice will absorb heat. It will become first 1 gram it will change. It will become half ice, it will become a part of ice water mix. That time okay, minus 10 degrees Celsius to 0 degrees Celsius ice, complete temperature change will be there. So that time state change will not be there. mc delta theta. Here specific heat capacity of ice is 1/2 calorie per gram degree centigrade. Okay, how much mass the temperature of how much mass is converted, that we will have to put here. How much temperature is we are changing, that we will have to put here. Then it will become ice at 0 degrees Celsius. First it will become -9, -8, -7, finally it will become 0. Once it becomes 0, then there will be change in state. So ice at 0 degrees Celsius will start converting into water. So 10 gram ice, now it will become 9 gram, 8 gram, 7 gram. Likewise, entire water will be converted. That time there will not be any change in temperature, but there will be change in state. Solid will become liquid. Okay, what is the energy required? Here it was mc delta theta, now it is m into L. L is what? Latent heat of fusion, constant for a particular material. For ice to water, water to ice, that is one value. For other materials like copper, iron, these values will be different. So this is the constant value for this 80. How much mass it converted, that we will have to multiply. Okay, now then what will happen? It will become ice water mix. Complete, after complete conversion, it will become 0 degrees Celsius water. Okay, so for full process, ml 800 calorie will be required. Now again, if we apply heat, this 0 degrees Celsius water, its temperature will slowly increase. 5 degrees Celsius, 10, 15, up to how much it can go? By maintaining as water, it can go up to 100 degrees Celsius. After 100 degrees Celsius, its state will change. Now water at 0 degrees Celsius will be converted into water at 100 degrees Celsius if we keep on applying heat. So what is the formula we will have to use here? Again mc delta theta. What is the specific heat capacity of water? Specific heat capacity of water is 1 gram per degree centigrade. Okay, so this is of water. Specific heat capacity of water is 1 calorie per gram degree centigrade. Okay, so once it becomes water at 100 degrees Celsius, again if we are applying heat, what will happen? This will become, this will convert into steam. So 1 gram of water will become steam, 2 gram of water will become steam. Likewise, complete water will become steam. What is the formula we need to use for state change? ml. What is the latent heat of vaporization or latent heat of condensation? 540. It is 536. We are using 540. So if only 5 gram is converted, 5 into 540. If 10 gram is converted, 10 into 540. Likewise, 5400 calories is required for entire water at 100 degrees Celsius to convert into steam at 100 degrees Celsius. Again, for steam to become steam at a higher temperature, again mc delta theta. So latent specific heat capacity of steam is 1 by 2 again, just like how we have taken here. There again we can take. Clear? Okay, if anything you want to note it down, pause the screen and note it down. Okay, see children, suppose the same process we can go back. The only difference is here we were supplying heat. Here what we need to take, we need to extract heat. We are taking heat from the steam. Steam is converted into water. We are extracting heat from the water. Temperature of water is decreasing. We are again extracting the heat from the water. The water slowly converting into ice. Again we are extracting heat. Water will completely convert into ice, again extracting heat. Ice will become ice at -10, -20, likewise -20 degrees Celsius. Okay, so only difference is in this process heat is given, in this process heat is taken. Okay, clear? Okay, shall I raise this? Okay, so I'll summarize. Okay, so for temperature change, the formula for heat given or heat released or heat absorbed, Q is equal to mc delta theta. What is this? This is specific heat capacity. Specific heat capacity. So C is equal to 1 by 2, C is equal to 1, C is equal to 1 by 2. This is for ice, water, steam. Okay. For this is one process in this overall. For phase change or state change, okay, the heat required or heat rejected, heat released or absorbed will be what? ml. What is this L? Latent heat. Okay, latent heat. And here latent heat of fusion or melting is equal to 80 calorie per gram in the case of what? Ice water. Okay, same way latent heat of vaporization or condensation is 540 calorie per gram. Actually originally this is 536. Okay, so what is this? Water and steam. Water and steam. When there is temperature change, the entire heat will be utilized for changing the temperature. When there is phase change, entire heat will be utilized to change the phase. So here the important thing is no temperature change. No temperature change. Clear? Note it down. Okay, shall I raise? Pause the screen and note it down. Okay, now suppose if we need to plot a graph of temperature and time t. Okay, so this is temperature, okay, and time t. Suppose if this is, say for example, minus 20 degrees Celsius, okay, this is a state water will be in the form of ice. We are considering here the normal temperature and pressure, that is at atmospheric pressure, 1 atmospheric pressure. Okay, we need not mix triple point here, we are considering the normal situation. Okay, so here if we are keep on applying heat, as the time moves, what will happen? Its temperature will keep on increasing, and what will happen? This will become ice at, this is 0 degrees Celsius for y-axis and 0 seconds for x-axis. So what is this? This is the slope. Okay, so this is at 20 degrees Celsius, now this is at 0 degrees Celsius. So here in this situation, what will be Q? Q will be mc delta theta. There is change in temperature. Then after that, for some time, okay, this is going to be ice water mix. After that, this water's temperature again it can rise up to how much? Up to 100 degrees Celsius. So we can say this is nothing but melting point. Okay, or fusion also will take place. So here this will be converted into water. The Q at this point is nothing but ml. Okay, the heat required is ml. In this process again Q is equal to mc delta theta. Once it becomes 100 degrees Celsius, then the conversion of water into steam will happen. So water steam mixture will be there at 100 degrees Celsius. Finally, suppose if this is A, this is B, this is C, this is D. At point D, entire water will be converted into steam. Again, what will happen? Once it becomes steam, again Q is equal to mc delta theta. So here this is going to be steam. At C, this is going to be water. Here water steam mix. So here this is going to be water. At A, this is going to be ice. Clear or what? So let us take this alpha, beta, gamma. Okay, let them be slopes. Okay, note it down. Okay, so now what is slope here? Suppose if we consider this point, okay, let us, this is what shall we put here? Okay, let us put x or something. Okay, xa, between x and a, this is slope. Slope is equal to tan alpha. So what is tan alpha? Tan alpha is nothing but the change in temperature. Okay, change in temperature. So delta theta divided by what? Change in time. Okay, change in time, delta t. Now what is power? Power P is equal to energy or heat by time, or Q is equal to P into T, we can say. Okay, so here if we take delta t, the change in time, this will become delta theta divided by tan alpha. Delta theta divided by tan alpha. Q is equal to mc delta theta. We can say delta theta is equal to q by mc. Q by mc. What about q? Q is actually p into t. So we can say delta theta is equal to q by mc. So p into t divided by mc. P into t divided by mc. So if we put here, this is also actually delta t. We can say this is also delta t. How much time is taken? No worries. Delta t we can put. Both are same. So delta theta divided by delta t is equal to what? P by mc. P by mc. So from this we should understand one thing, like slope is inversely proportional to the specific heat. Slope is inversely proportional to specific heat. Okay, so same thing will happen with the beta, same thing will happen with the gamma also. Okay, so children, slope is inversely proportional to specific heat when you plot temperature time or temperature heat graph also. Whatever graph if we plot, we will be getting like this. Clear? Fine. And here slope is 0. Here slope is 0. So specific heat is inversely proportional to slope. Clear? Shall I erase this? Okay, so here in calorimetry, heat lost is equal to heat gained. So if we mix two substances, like if we are pouring water at 100 degrees Celsius into a copper vessel at 50 degrees Celsius, what will happen? Water will give heat to that copper vessel, and copper vessel will absorb heat from water. So the temperature of copper vessel will increase and temperature of water will decrease. Finally, thermal equilibrium will be there. So this mix will happen between water and copper vessel, between water and water, between water and something else. Okay, any mix can happen. There will be mix of ice and steam, ice and water, water and steam. All these things are there. Okay, so carefully handling by applying these two concepts, okay, of latent heat and specific heat capacity, we will be able to solve the problems. One more thing which we need to understand here, it is nothing but water equivalent. Okay, so this water equivalent is nothing but how much water, okay, will give same amount of heat of some other substance. Say for example this mass of copper and specific heat capacity of copper into the change in temperature in copper. This is equal to mass of water, specific heat capacity of water into that much change in the water. So when we take like this, this delta theta can be cancelled, and mass of water will become what? Mass of copper into specific heat capacity of copper. Okay, so here mass of water is nothing but mass of the copper into the specific heat capacity of copper divided by a specific heat capacity of water. Okay, so the thing is, like instead of giving copper as the data, they will be given like the equivalent mass of water for the same heat of copper. Okay, so instead of giving data of copper, they will be giving mass of water. Okay, so that is called the water equivalent. So instead of calculating using some other substance and its specific heat capacity, we will be comfortable in handling with the water. So they will be giving that a water equivalent of this substance is so and so. So then that mass will be given, then remaining things will be easy. We will be just solving, just like how do we solve for water. Okay, so that is what is water equivalent. Okay, so this specific heat capacity is for 1 gram. Okay, for 1 gram, what specific heat capacity? Specific heat capacity C is equal to the heat required for 1 gram per unit degree change in the temperature. Okay, so there is slight difference between specific heat capacity and heat capacity. Heat capacity is actually M into C, that is not per unit mass. Okay, this is for mass M. So heat capacity is nothing but mass into specific heat capacity. Specific heat capacity is total energy per unit mass per unit degree change in temperature. Okay, such a difference is there. This one is constant. This is constant, but here this mass is variable. This mass is variable, so this is not constant. Okay, clear or what? Okay, so with this many concepts we will be able to do problems. By doing problems, varieties of problems are there. We will have to make what? We need to dominate the topic. Okay children, okay, thank you so much, goodbye, good luck. We will meet in the session for doing problems.